So today's lesson is going to be the first lesson in Unit 4. It's in Section 2-3, and it will be over rates of change, which is really most specifically velocity and what we call margins. So we're looking at these today. If you have any questions, you have got to text me. So the first thing that we're going to look at is average rate of change. Average rate of change is really no different than finding a normal slope. As you can see, I'm going to try to make this picture bigger. All right, so there we go. So as we look at this picture here, you can see that the distance between the y values, so this is one ordered pair, b is our x value, f of b is your y value, and this is our other ordered pair, a is your x value, f of a is our y value. So this distance represents your change in y, so the difference between the inputs, and this distance right here represents your change in x's. So average rate of change is really no different than the difference between your y's over the difference between your x's, change in x over change in y. So it's really a nothing new concept. So as we look at this particular problem, try to make it a smidgy bit bigger. All right. The concept, so you're going to have several word problems in this particular section, but don't let them bother you. They all really rely upon the same types of formulas. So this particular problem talks about the concentration C, which is going to be our y value, in milligrams per milliliter of a drug in a patient's bloodstream, is monitored over a 10-minute interval for 2 hours, where t is your time in minutes, as shown in this table here. So we have various different times, so every 10 minutes we're taking account of the concentration of whatever this drug is in this person's blood system. And so we're going to look at the average rate of change from various points in time. So this interval right here goes from 0 to 10. These intervals are always on the x value. So it means from 0 time to 10 minutes, from 0 time to 20 minutes, from 100 minutes to 110 minutes. So we're going to look at each of these separately. And so you might hear my pug barking. She's mad that I have relegated her to the back bedroom because she's too loud. All right, so for A, I am going to look at for 0, 10, I'm going to have to get the ordered pairs. So for the first ordered pair, I'm going to take my time of 0 right here, and its y value associated with that time of 0 is 0. So I get the ordered pair of 0, 0. And that gives me t sub 1 and t sub 2. Then I'm going to get a second ordered pair using 10 as my time. So my first x value is going to be 10. But looking at the chart, 10 and 2, that's my next order pair. So 2 is the y value that goes with the 10. And so this gives us our, I don't know why I put t on this other one. Let me see if I can erase it. Sometimes I can, sometimes I can't. Oh, and it's not going to let me. Well, in that case, this is supposed to be c sub 1. Sorry about that. So this is our t sub 2 over here and our c sub 2. I did that on my notes too. Whoops. So then we're going to find our change, our average rate of change. So it's going to take our y's, which would be our change in c, over our change in t. And so I'm just going to set up a template so it looks like a normal slope template. And I'm going to take my c value. So I'm going to start with 2, the second c value. You always want to take the rightermost value and subtract the leftmost value if you're thinking on the x-axis. So the rightmost x value is our 10. So I'm going to take its y value of 2. And it goes here. So I guess maybe I'll write this up here for y'all. So the formula that I'm using right here is going to be c sub 2 minus c sub 1 over t sub 2 minus T sub 1. So that's what you see me putting in here. So my C sub 2 is 2, my C sub 1 is 0, my T sub 2 is 10, and my T sub 1 is 0. So that gives me 2 over 10, which is 1/5. And it's a word problem, so we're going to convert that to its decimal form, which is 2/10 milligrams per minute. So this is our first solution. So between the interval from 0 to 10, our average rate of change is 0.2 milligrams per minute. So that means, because it's a positive value, that means that the concentration in this person's blood system of this particular drug has gone up. So it's increased because it's a positive value. So now let's look at the second interval. So the second interval is from 0 to 20. So again, we need to get our ordered pairs from the table. So 0 is my first X value, so that's 0. And then according to the table, as we used before, the Y value is going to be C. So this is going to give me my T sub 1 and my C sub 1. My second ordered pair, starting with a T value of 20, which is my first X value, according to the table here, the 17 goes with that T value. And so this is going to give us our T sub 2 and our H sub 2. And so we're going to put that in our formula. So change in C over change in T. And then we're just going to put our values in. So our C sub 2, oh, I put H. You know what? I'm having issues today. It's because I haven't taught in front of you guys for so long. So my C sub 2, God bless the coronavirus and distance learning. All right, so my C sub 2 is 17. My C sub 1 is 0. My T sub 2 is 20. And my T sub 1 is 0. So that gives me a value of 17 over 20. And if I put that in my calculator and I get a decimal equivalency, actually I think it's exactly equal to this, 0.85, so 85/100ths milligrams per minute. So you can see that the concentration has continued to go up. It's another positive value, and it's a higher positive value. So in this case, the concentration is still increasing, and it's increasing at a more rapid rate per minute. And then we're going to look at our last interval, which is 100, 110. So to get my ordered pairs, again, I'm just looking at the table. So I'm going to start with my first X value, which is 100. And according to the table, 113 goes with 100. And then my second X value is going to be 110. And according to my table, 103 goes with 110. And so this gives me my T sub 1, C sub 1, T sub 2, C sub 2. And it is important that you go in the correct order, because your positives and negatives are going to tell you whether the concentration is increasing or decreasing. And so if you're a nurse or a doctor and this is your patient and you've put the wrong ordered pair first, you're going to think that the concentration is decreasing when it should be, when it's increasing, and that's going to affect how you care for this patient. So order is important. So change in C over change in T is equal to, and so our C sub 2 is 103, C sub 1 is 113, so this one's going to give us a negative value. T sub 2 is 110, and T sub 1 is 100. And so I end up with a negative 10 over 10, which is negative 1. So that means that we have negative 1 milligrams per minute. And as I stated, because it's negative, that means that the concentration is decreasing in this person's bloodstream. Okay, so next you get a try. So what I want you to do at this point is to pause the video, and I want you to use the table that we just had in example 1, and I want you to find the average rate of change over these intervals that I've chosen here for you. So pause the video, and you do it on your own, then restart the video. Okay, so hopefully you paused the video, and so you will have wanted to get your ordered pairs off the table. And so for 90, you should have gotten 90 and 113. And for 100, you should have gotten 100 and 113. So this is our T sub 1, C sub 1, T sub 2, C sub 2. So our change in C over change in T. So we're going to put 113 here. C sub 1 is 113, T sub 2 is 100, and T sub 1 is 90. And so we end up with 0 over 10, which is 0 milligrams per minute. Minute, second. I think I put minute on my notes. Oh yeah, it is minutes. Okay, per minute. Oh yeah, because we're looking at it in minutes. All right, so then there was no change for this person in this particular 10-minute interval. No change in the concentration, so it remained the same as the previous interval. All right, so then for this interval, from 0 time to 120, which is the overall time that we were looking at this patient. So we're going to start with 0, 0, and then the 120 pairs up with 68. So this is T sub 1, C sub 1, T sub 2, and C sub 2. So change in C over change in T. And then our C sub 2 is 68 minus 0. T sub 2 is 120 minus 0, which gives us 68 over 120, which reduces to 17 over 30, and its decimal equivalency is approximately 0.57, so 57 hundredths milligrams per minute. So overall, the drug did increase in concentration in this patient's bloodstream. Next, we're going to look at average velocity. So average velocity, these aren't subtraction signs, it's just the way I had to put it into my smartboard presentation, but it's just the change in time over the change in distance over the change in time. So you could even write it as change in distance over change in time. Remember, time is always our x value because we cannot affect time, and the distance depends upon time. So we really still have our change in y over change in x. And then one thing I do want you to note, that if the average velocity is negative, it means the object is moving downward. So in this case, negative means down, velocity is moving in a negative direction, and positive would be it's moving up. So let's look at a few problems. So we're going to find an average velocity of a free-falling object. So this would be an object where somebody has dropped it. There's no initial velocity. They're not throwing it with any kind of force or speed. They're just literally holding it out and dropping it, like you might just hold out a tennis ball and drop it. So I'm going to draw a little picture above here to kind of give you an idea of what I'm talking about. So like here's the ground, and here's a really tall building with some windows. Okay, maybe not so tall. Tall enough for me. Here's my blue man. And then he is holding out, I don't know, some object. And this happens to be at 100 feet from the ground. And then he is going to drop said object straight down. He's just going to drop it. He's not throwing it, nothing. He's just letting go of his hand and letting it drop. So the other thing I want you to note is that one of the things that I've highlighted here is that it's a free-falling object. It's dropped from a height of 100 feet, so that's where that 100 comes from here to here. And the air resistance is neglected. In other words, we're ignoring it. So oftentimes when modeling a falling object, you have to be able to decide whether to account for air resistance or not, because air resistance definitely can affect velocity, like a headwind and a tailwind would. But in this case, we're going to simplify things and just say that basically it's being dropped in still air. And so that's why that's important for them to say that. Then the height in feet of the object at t times in seconds is given by this equation here. And so I'm going to go over how to come up with this equation on your own. But this negative 16 in front of the t squared is always there because it's the force of gravity when we're dealing with feet. So force of gravity when dealing with feet, typically by seconds. Well, always by seconds. This happens to be the height of which we dropped that object. And because there is no initial velocity, you notice that we're missing our middle term, our t term. I'll get into that a little bit more in a minute. But this is the function that we're going to use right now. So let me highlight that. We'll put a box around it. Okay, so we're going to find the average velocity of the object over each of these intervals from time of 1 second to 2 seconds, 1 second to 1.5 seconds, and 1 second to 1.1 second. So what we're doing is we're actually getting closer and closer to 1. So the 1 and 2 seconds are the furthest time apart that we're looking at. This is just a difference of a half a second, and this is a difference of a tenth of a second. So I want you to see what happens to the average velocity when we're dropping something, and think about what gravity does, because what it starts here at an average velocity of 0, and it ends up here after a certain amount of time with the fastest velocity of all. So in between here, there'll be smaller and smaller velocities. So we're just going to do the same thing that we did before. So we're going to find our ordered pairs. So from the 1, but this time I'm not looking at a table of values. I do know my x value is going to be 1, but I have to take this x value of 1 and plug it into this equation. So I highly suggest that you put this into the y equals right here of your calculator and go to the table feature of your calculator and let it do the work for you. So when I put in 1, my y value, which is my height, turned out to be 84. So after 1 second, we had a height of 84. And then after 2 seconds, when you plug it into the function here, right here, I plugged in 2 in for t squared. After 2 seconds, we had a height of 36, which makes sense. The more time goes on, our height should get smaller and smaller, right? So then this is going to be our t sub 1, and this is our h sub 1, t sub 2, h sub 2. Draw a line here. And then the formula that we're essentially using for our average velocity, remember it's your change in distance over your change in time. So my change in distance, so I've got change in height, and then over my change in time. I'm going to put in my values. So remember, your h sub 2 has to come first. So it's important, order is important here. So the 36 comes first, and then the 84, and then the 2, and then the 1. And so what we end up with is negative 48 over 1, which means that it is negative 48 feet per second. So remember what I said earlier, that the fact that our velocity is negative, our average velocity is negative, means that the object is moving downward, which is what it's doing. So perfect, that's what we wanted. All right, so then let's look at what happens in our next time interval. So at a time of 1, so we have 1, plug this into your function right here, plug 1 in here, and you will get a y value of 84. We did that before in the last interval. And then here, if you put 1.5 into the function, you will get 64. And so this becomes our t sub 1, h sub 1, t sub 2, and h sub 2. And so we're going to find change in h over change in t equals. And then plug our values in. So I've got 64 minus 84, and then 1.5 minus 1. So that gives me values of negative 20 over 0.5, which gives me a total amount of negative 40 feet per second. So as you can see, right here, this is a longer time period between time values. So from 1 second to 2 seconds, we had an average velocity of negative 48. But at 1 second to 1.5 seconds, less time, we didn't have as much velocity, because remember that gravity is going to pull on that object and create the velocity to go faster. All right, so you should be thinking to yourself, what do I expect for this next one? Since it's the smallest interval of time possible, I expect that my answer is going to be less than negative 40. So here we go. Let's find our ordered pairs. So for 1, as we've had all along, we have 184. So that's the same as all of them. And then for 1.1, we have 1.1. And plug that in, you get 80.64. 80.64. So we have our t sub 1, h sub 1, t sub 2, h sub 2. And so our change in h over our change in time. All right, then our 80.64 goes first, and then 84, and then 1.1, and then 1. So we end up with negative 3.36 over 0.1, which is equal to negative 33.6 feet per second. So of course my pug, I don't know if you can hear her barking in the background. She's said literally nothing all day because she has slept all day. And now as soon as I want to make a video, she's barking constantly. Oh, gotta love the pug. All right, so you try it. So this one's on your own. Again, pause the video. And then I want you to note, though, before you pause the video, that the equation has changed. The 180 is different from the previous one. You previously had 100 there. This is 180. So please make sure you account for that change. Now pause the video and then restart it when you're done. So find your ordered pairs. So when time is 0, our height was 0, which that makes sense. Or I'm sorry, that would be wrong. Wrong. Clearly not. We're dropping it. So my bad. I do have it correct in my notes. So at time 0, we are dropping it from 180 feet. So that's our height. And then at 1 second, when you plug it into the formula here, that's where you're plugging in your values, you get 164. So this is your t sub 1, h sub 1, t sub 2, h sub 2. So our change in h over change in t, put in our values 164, 180, 1 and 0, gave us values of negative 16 over 1, which means it's negative 16 feet per second. So that's our average velocity over that 1 second interval. Okay, so then for the second one, at a time of 2, you have 2 with a height of 116. And at a time of 3, you have time of 3 and height of 36. So this is our t sub 1, h sub 1, t sub 2, that's a 2, h sub 2, change in h over change in time. Plug in your values, 36 minus 116, and 3 minus 2. And so you ended up with negative 80 over 1, which is negative 80 feet per second. So we have a rather quick velocity there. And as you can see, we don't have much height left. And so the closer you get to the ground, 0, the faster this velocity is going to be. So good job. So what about instantaneous rate of change? In other words, what is the velocity at a specific point in time, not over an interval of time? So this is going to give us the exact rate of change or the exact velocity at any moment in time. And of course, it's going to involve the derivative. So as you can see here, finding the limit of that slope is going to give us, and you've seen this difference quotient before. I'm not going to make you do the difference quotient. I'm not going to make you use the limit definition. We're going to use our own knowledge of quick shortcuts to find the derivative, but that's what we're going to do. So the rate of change, the instantaneous rate of change, is just the derivative of the original function. So here we go. So example 3 says find the velocity of the object in example 2. So we'll go back and use the same original function from example 2, and we're going to look specifically at time is equal to 1 second. So there are 3 steps to this. So step 1. Step 1, we're going to find, well, the height of the object falling in example 2 is given by and so this is the formula h equals negative 16t squared plus 100. So this is called our position function. All right, so then step 2, we are going to find the derivative of the h function, which is our position function. Okay, so we're going to, let me see, I'd like to get a pretty color. I don't have the option. Oh wait, yes I do. Give me a moment. All right, here we go. So, all right, so our derivative, we're going to call it h prime of t. So there's our derivative. And so remember, we're just taking 2 times negative 16 and reducing that by 1, and the derivative of a constant is 0. So our derivative is quite simply negative 32t. That's it. So this is called our velocity function. Or, yeah, our velocity function. Okay, so then part 3, so once you have your velocity function, now at any point in time, this is going to give me my instantaneous velocity at any point in time. So we're going to plug that 1 into the function, the derivative function here. So find the velocity. At t equals 1. Okay, so I'm going to take okay, I'm going to do h prime of and plug my value in. let's make it, I don't know, make it green. All right, so I'm going to put 1 in here and 1 in here. So h prime of 1 is equal to negative 32. And so what does that mean? Therefore, the velocity at 1 second is 32 feet per second downward. How do I know it's downward? Because my velocity is negative. Oops. I'm gonna put a box around it and we're done. All right, you try it. So I want you to pause the video and I want you to find the velocity. Now, mind you, before you pause the video, I've changed the problem on you again. I've changed it to the function for the you try it for exercise 2, which changed to that 180. So you're going to find the velocity at 2 different times. So pause the video and find those 2 different velocities, if I can talk today. All right, so A, we're going to find velocity at t equals 1.75 seconds. So we're going to use our height, and then we're just going to find the derivative. So, and I'm going to use the same derivative in the next part. So h prime of t is equal to negative 32t. So just like in our previous example, because it doesn't matter at what point you're dropping it, the instantaneous velocity is still found the same way. So then we're going to plug into this our seconds of 1.75. Okay, and so using our handy dandy calculator, we get negative 56 feet per second, which is different than an average over a time interval. This is exactly when we click the stopwatch at 1.75 seconds, this is going to be the exact value at that point in time. So then part B is your velocity at t equals 2 seconds. Now this time we don't have to find the derivative because we found it. So h prime of 2 is equal to negative 32 times 2. So that is equal to negative 64 feet per second at exactly 2 seconds. Okay, so there's a difference between the average rate of change versus instantaneous velocity. Average rate of change is velocity over a time interval, whereas instantaneous velocity uses the derivative and it is the exact velocity at that point in time. So make sure that you know the difference when you're reading your problems. Okay, so general position function. So I told you we were going to talk about this later. Sorry if I'm making you sick. Boom, there we go. Just trying to make it a little bit bigger. So you've seen a portion of this formula, give or take, in each of these problems that we've done. This has remained the same. This is when we're using feet per second. It would change if we were doing meters per second. And so this is just the force of gravity. V sub 0, as I have written here, and so you might want to do some highlighting. So V sub 0 is the initial velocity in feet per second. So right here, when you're told the initial velocity, that's what somebody's throwing an object with. That's the force of that object. So if I say that I have an initial velocity of 20 feet per second, you're going to put that amount there. And then the h sub 0 is the initial height in feet. And so if we are throwing something from particular height above, you'll have a height, whatever the height is. So if I'm throwing something from 20 feet, that's going to be 20 feet. If I'm throwing something from the ground, then that would be a height of 0. So just pay attention to what your initial height is and what your initial velocity, and then you can create your own equation. And then the last thing we have here is that the derivative, so the derivative of this whole function is always going to be negative 32t plus whatever your initial velocity is, because that would be 1 times that value. And so that's going to be your instantaneous velocity function at any point in time. So our last example is example 4, and of course you have a try it after that, so don't get too excited. I'm going to make that a little bit bigger. So we're going to find the velocity of a diver. So I'm going to draw a cute little picture. Let me pull this down just a smidgy and make it straight. Doesn't that bother you? It's crooked? Well, it bothers me. Yep, there we go. All right, so I have some water. So here's some water. And I have a dive board. I'm a really excellent artist, y'all. Okay, more like a platform. Whatever. And then I have a diver that jumped off, and my diver is going to be, let's give my diver a color, red. I'm going to make my diver red. So there's my diver. And then in this particular case, this is 32 feet from here to here, okay? And, oh, my diver is clearly going in this direction, so I'll put an arrow that way. All right, so at time t0, a diver jumps from a diving board. So this is time t0, and the board is 32 feet high, so that's why I put 32 feet here. This isn't a parabolic arc, so that's why we're using our general position function, which is a quadratic function. And so they tell you a couple of things. So I know that my initial height is 32 feet high. So that's going to go in place of h sub 0. So I know I'm at the very end, I'm going to have a positive 32 because I'm coming from a positive height. And then the diver's initial velocity is 16 feet per second. So that's going to go here. And because, well, your initial velocity is nearly always going to be positive. I'm trying to think of a situation when it's not at this moment that you would understand. But for right now, it should always be positive. And so I have positive 16t, positive 32, and then of course, it's always negative 16t squared. And so that's h equals. So we're going to use h equals, I'll write it pretty up here, negative 16t squared, plus the initial velocity is 16t, plus the initial height is 32. So this is the position formula that we're going to use. So the first question says, when does the diver hit the water? So the water has a time, the water has a height of 0, so you will let h equal 0. So for part A, we are going to let h equal 0 and set it equal to negative 16t squared plus 16t plus 32. And then all of your algebra skills come into play. We're going to solve for t. So I am going to use factoring. I happen to know that negative 16 can factor out of each of these terms. So I'm going to divide each of these terms here by negative 16. And so I get positive t squared, negative t, because you divide a positive by a negative, get a negative. And then 32 divided by negative 16 is negative 2. And so this function factors as t minus 2, t plus 1. Set t minus 2 equal to 0 and t plus 1 equal to 0. You get t equals 2. and t equals -1. Well, t equals -1 does not make a lot of sense because we shouldn't have negative time, and that comes from the fact that right here we didn't start at a height of 0. We started at a height of 32. So all of this down here, which would finish that parabolic arc, is going to be in negative time. So that's why we're going to throw that out. The problem doesn't understand really that we started from that height in reality. Then our answer is it will take, I'll write it out here, I guess. So therefore, the diver will hit the water in 2 seconds. So that's the answer to the first part. I'm still trying to get over being sick. And then the second part, B, is what is the diver's velocity at impact? So that's an instantaneous velocity. So an instantaneous velocity means that we want to find the derivative. So the derivative, so h prime of t, is going to equal -32 t plus the initial velocity of 16. So then we are going to just plug in our time of 2 seconds from what we found out above. So how do I know I'm putting in 2? Well, it wants to know what is the diver's velocity at impact. Well, at impact is when they're hitting the water. And so we knew it took them 2 seconds to hit that water. So that's why I'm using the 2 seconds here. And so then negative, change my color, -32. Plug in your 2. And then you get a total of -48, and that would be feet per second. So therefore, the diver's velocity at impact is -48 feet per second. So that, again, that -48, remember, means that the diver was going downward. And you could say, therefore, the driver's velocity at impact is 48 feet per second downward. If you don't want to write that negative, I'll accept that. That's fine. All right, last problem, you try it. So you need to pause the video, but remember, you have to find your own general position function first. So you're not going to be using the same one that we just used. So use the information to find your own general position function, and then restart the video and check to see if you're right. All right, good luck. So I did note here that the diver's initial velocity is 16 feet per second, and that's upward. So I guess if they just fell down and didn't do any parabolic arc upward, there's where your negative would be. But because the diver is jumping upward, their initial velocity is 16 feet per second, so that's a positive amount. And then their initial height is 32. So in this one, the diver jumps from a board 12 feet high, and with that same initial velocity of 16 feet per second. So the only thing that's going to change is this 12 feet. So your position function, part A, should be h equals, and so then it's -16 t squared, as they always are, but because the initial velocity is positive, we've got a positive 16t, and then the initial height was 12, so plus 12. So this is the first thing that the question asked you for, so good job if you got that. And then part B, the velocity function. So then we're just going to take the derivative of part A. So h prime of t is equal to negative 32t plus 16. So that did not change from the example that we just did. And so that's all I have for you. So please complete your homework. If you have any questions about these notes, text me. And if you have any questions about the homework problems that I assigned you, please don't hesitate to ask. If you don't ask, you're never going to know. And you do have a major grade test over this when we return. So good luck.